Imagine your email inbox flooded with a ton of emails where some are important and some are just spam. How does your email filter know which ones to mark as spam? It's not magic, it's mathematics. Support vector machines or SVMs tackle this challenge by finding the perfect boundary between spam and important emails. Today, we'll explore how SVM work by focusing on the most critical data points. We will not only build intuition for it, but this and the following video are the only two videos you need to understand the fundamental mathematics behind support vector machines. In this video, we will talk about decision boundaries, the widest street approach, and we will also do an introductory lecture on constraint optimization, which by the way is going to be very essential as we go deeper into the mathematics of SVMs. So let's get started. So let's start. What is a decision boundary? A decision boundary is a dividing line, curve, or any surface that divides one class from the other. Let's say you have different data points and different classes. A decision boundary is something that separates these two out. And you might ask, well, how do you draw the best decision boundary? And that's a very important question, and that's the key question that we'll try to answer. Let's say you have two classes depicted here in negative and positive. We want a surface that differentiates these two, and when we get a new point, we are either able to classify it as positive or negative. We don't want to misclassify. So essentially, we are trying to solve a classification problem, and specifically two-class classification where the classes are linearly separable. Again, the example that I have here in the first graph, this is what we are trying to solve. Keep that problem statement in mind. But let's see if we can extend this to multiple classes. Now, what happens when we extend the concept of decision boundaries to multiple classes? This is where OVO, one versus one, and OVR, one versus rest, approach comes to play. In OVO, let's say we have n classes. We pick two classes out of it. So we have NC2 combinations. And for each of those two combinations, we build a classifier. So in total, we have n-1 by 2 classifiers, each trained on data from two classes. So imagine a classroom of students where every pair of student has their own game rules. Let's say they are playing by some rules where the rules can be analyzing how they compete and how they interact. And then you build out rules for each pair of students and analyze their interactions independently. In contrast, in OVR, which is one versus rest, you have n classes and we build n binary classifiers. So each classifier separates one class from all the others. Both strategies aim to simplify the complex problem of multi-class classification. So essentially, if we have solved for two-class classification, we have solved for multi-class classification. Now I want you to keep that in mind. But what happens when data isn't neatly classifiable in two dimensions? Imagine a circle enclosing data points that aren't linearly separable. This is where higher dimension spaces come into play, where mapping the data into higher dimensions can make them linearly separable. In this example, we do a transformation of the data points into the z-axis, which clearly helps us draw a plane in 2D to separate these classes out. This is called the kernel trick. We transform the data into a higher dimension so that they can be separated linearly. So let's bring our focus back to the two-class classification problem, which forms the basis for multi-class problems. So now we know that two-class classifiers can be extended to multiple classes, and we also know if there is non-linearity in separation of data points, that can be resolved through the kernel trick. So essentially, if we master solving the initial problem that we had, which was linearly separable two-class classification, then we can extend the same formulation to more complex cases by 1 and 2. And that's the key point here. So let's focus on solving this first example that we had, which is linearly separable two-class classification. The beauty of SVM comes from the fact that with the support vectors, we not only aim to find the best hyperplane, but also the widest possible margin separating those two classes. Let's say we have a data point scattered on a graph. Imagine two parallel streets running through our data points, each street touching near the edges of different class. Our goal is to find the widest street possible between the two classes without encroaching on any data points. This street represents the maximum margin separator, and that's the concept of Widest Street Approach in SVMs. Now that we have done some groundwork, Let's go deeper into the mathematics of the two class classifiers. So we'll take the same example that we started with, and this one. This is linearly separable two-dimensional data with two classes, positive and negative. Consider each data point as a vector in space, and now for an unknown incoming vector, we have to determine what class would it belong to. Now what we do, let's say this black dotted line is your hyperplane. We draw a perpendicular vector W, and we don't know anything about W's length, but let's say we draw a vector which is perpendicular to the hyperplane and call it W. And now this unknown point U is something that we have, and we have to determine its class. Let's say it lies on the other side of the hyperplane, which is the positive side. So what we can claim is the projection of U on W, which is the length, perpendicular length U has in the direction perpendicular to the hyperplane, that should be greater than or equal to some constant C. Why are we saying that? Because we want it to lie on the positive side, on the other side of the hyperplane. So we claim that, okay, the dot product should be greater than or equal to some constant C. And if we rewrite this equation as B is equal to negative C, we can claim W dot U plus B is greater than or equal to 0. But still, there are a lot of choices for W and B. These conditions are not very robust. So we have to make them a little more tighter, and let's impose more conditions with the dataset that we have. So let's say for positive samples, we claim that W dot X plus B is greater than or equal to 1, and W dot X negative plus B is less than or equal to negative 1. And this is something that we are claiming for a dataset, that if a data point is on the positive side, if it's classified as a positive sample, it should be greater than or equal to 1. And if it's on the negative side, it should be less than or equal to negative 1. Now the same thing can be written as yi times W dot xi plus B is greater than or equal to 1. What we have done is just encapsulated both of these equations into one single equation by introducing a mathematical convenience called yi, and yi can take the value plus 1 for positive samples, and it can take the value of negative 1 for negative samples. So essentially the final equation that we have becomes something like this. But if you look closely, we have not talked about one thing. We have not yet talked about what happens if a point lies on the boundary. And let's say if points are lying on the boundary, we want to impose additional condition on the boundaries as W dot X plus B is equal to 1 and W dot X negative plus B is minus 1. So if my point lies on the positive boundary, the first equation should hold, and if my point lies on the negative side of the boundary, the second equation should hold. These equalities should hold when we are on the boundary condition. And these mathematical constructs stabilize our boundaries and offer resilience and flexibility to our model. So these are all the conditions that we have imposed on how the data points should behave. Now let's calculate the width of these margins. So what we have right now is we have defined all the boundary conditions, all the conditions that we want to impose on W and B. So width can be written in terms of these boundary parameters x plus and x minus, and through these two vectors, we can say this blue dotted line is equal to x plus minus x minus. Now, if I have to calculate the width, remember that we have a vector W, which is perpendicular to the hyperplane. Using that W, we can say that the width is nothing but the projection of this blue dotted line, which is x plus minus x minus on W, right? So we are projecting this on W, or in other words, we are taking a dot product of this with W hat, which is the direction of W. If we simplify this, so can we simplify this further? Yes, we have these two boundary conditions that we imposed. And if we use these, we can say W dot X plus is equal to 1 minus B, whereas W minus X negative is negative 1 negative B, which simplifies this equation further to 2 over norm of W. And norm of W is the length of the W vector. So essentially what we did is we formalized the width as 2 over norm W. Now, let's take a moment to revisit where we are headed. The essence of SVM revolves around maximizing that crucial boundary, which is the width of the margin in our case. This goal shapes the entire model, steering all the decisions regarding data classification. Our challenge is to identify the optimal vector W and the bias term B so that the margin is wide enough. Therefore, a problem statement reduces to something like maximize 2 over norm w given the constraints yi times w dot xi plus b is greater than equal to 1. Now this has converted into a constraint optimization problem. If let's say we didn't have any constraints, we could just take the function that we had and differentiate and put the derivative to 0 to find the optimal values of that function. But in this case, since we have a lot of constraints, we'll have to use constraint optimization on multivariate calculus to do this. And there are some neat tricks in the bag for multivariate calculus when you have constraint optimization. So we are going to take a detour from this problem and we are going to take another problem which is a very simpler problem compared to this one. And in this problem, we will try to formalize how we can maximize a certain function given certain constraints. And using that tricks and using those methods, we will come back again to our SVM problem and apply all the mathematics on it. So this motivation is very important, that we understand where this constraint optimization problem is coming from and we are able to appreciate how we are going to solve this. So let's visualize the function f of xy. And if I draw a parallel plane to the xy plane, I have constant z value, or in other words, places where the function remain constant. This constant plane intersects with the function and the line of intersection is called a contour line. As you can also see in this particular graph, there's one line of contour that's coming out from a certain z value. This is the line where the value of the function remains same. Now let's draw multiple contour lines of the function f on the xy plane, and let's also visualize the function g of xy, which is our constraint. In this case, our constraint is a circle with unit radius. So we have to find the maximum value of f from all the set of points where the contour are intersecting with a unit circle. Take a moment to think about that. If you observe closely, the maximum point will occur where the function f and g are tangent to each other. Or, in other words, the gradient of f and g are in the same direction. The gradient is nothing but a vector with partial derivatives of a multivariate function. It's just a way we can generalize derivatives for higher dimensions. So that's the key insight here. The gradient of f and g are in the same direction. So if the gradient of f and g are in the same direction, we can also write it as gradient of f is equal to lambda times gradient of g for some constant lambda. Right? So we have just written the gradients in this form. So we know that both f and g are two-dimensional functions, which is they have x and y variables. So we can expand it in the matrix form as partial derivative of f with respect to x and partial derivative of f with respect to y. So these are essentially two equations written in matrix form. And once we have this, what we can do is, let's say we have the form of g, which was a unit circle, but let's say it has some radius. Now let's say it doesn't have to be a unit circle. It has a radius of c, whatever it is. So we can rewrite g in the form where g of xy is x square plus y square is equal to some constant c. So we have just rewritten g in a different way. And let's also define another function called Lagrangian. Now, it will become clearer why we are defining it in this way, where Lagrangian is a function that we define in x, y, and lambda. Remember the lambda, that constant that we introduced here? Let's just say that Lagrangian is a function which is written as f minus lambda times g and the constant. So f minus lambda times your constraint equation. Now, why are we using this form? Why are we defining a function called Lagrangian, which is of this particular form? And the reason is that if you wanted to find the extremum of Lagrangian, which is maxima or minima for the Lagrangian function, we can just take the gradient of the Lagrangian and put it to 0, right? That's how we find the extremums of any function. So let's just do that. Let's put the gradient of L is equal to 0. And when we do that, the first two equations that pop out. So remember the form of Lagrangian is, it is a function in x, y, and lambda. So we'll take three partial derivatives with x, y, and lambda respectively and put it to 0. And if you see the first two functions, when we take a partial derivative with respect to x, this becomes dou f by dou x, and the second term becomes dou g by dou x times lambda, and c is a constant, so it is 0. The partial derivative with respect to x is 0. So what does the first two equations translate to? They become the conditions that hold true at the extremums of f and g. So when we are trying to find the value of extreme value of f given the constraint g, the equation that comes out in that scenario is the same when we put the Lagrangian's gradient to 0. So the first two equations denote that. And then the third equation is the derivative of L with respect to lambda. And when I do that, I am only left with g minus c. So g of xy minus c. And this is the condition or the constraint that we have to follow in constraint optimization problem. So what just happened? So I just redefined and I defined a new function called L. And now what I've done by doing that is the constraint optimization problem that I had, where I have to find the maxima of f given the constraint g. That problem has reduced to an unconstrained optimization where I just have to maximize the Lagrangian and there are no constraints. Now think about this problem for a minute and try to see what happens if we replace the variable x with the w vector and the variable y with the bias term that we have in support vector machines. Can we formalize the Lagrangian in support vector machines, and can it help us optimize the value for w and v? And that's the question that we'll try to solve in the next video. But this is the motivation of why we are doing things in this particular way. Because constraint optimization requires the formulation of Lagrangian, which is a mathematical convenience that helps us reduce a constraint optimization to an unconstrained problem. So that's all for this video. And I would urge you to think a little bit more about how you would formulate the Lagrangian for support vector machines. And that's what we'll do in the next video. So stay tuned and I hope you enjoyed this video. Thank you so much.